At 3 a.m., the world is quieter. The streets are empty, the wind is softer, and thoughts slow down. It's a time when the mind drifts, neither fully awake nor asleep. Our journey leads us into the hidden world of the forest, shifting from day into night. When light fades, the forest changes. Shadows thicken, mist rises from the ground, and every branch becomes a path for silent wanderers. The darkness does not end the forest's story. It reveals another chapter, alive in every shadow and sound. So let yourself sink into the silence, dim the lights, close your eyes if you like, and let your thoughts trail off like spores in a breeze. Because at 3 a.m., even the smallest things deserve to be seen. When daylight fades in the forest, the change comes quietly. The last warmth lingers in the canopy, shimmering on leaves and branches that still hold the glow of the sun. Birds exchange their final calls, scattered notes drifting like fragments of a song soon forgotten. Then, one by one, familiar daytime voices fall silent. The bees vanish from their blossoms, the chatter of squirrels ceases, and the steady hum of insects weakens, as if a curtain were being drawn across the soundscape. This is not silence in the strict sense, but a transformation. The rhythm of the forest shifts into a slower register, softer, deeper, as though the whole landscape is inhaling before the long exhale of the night. What to human ears may seem a loss of sound is, in truth, the preparation of a new chorus, a world awaiting its turn to speak. The light, too, changes its character. The warm hues of dusk dissolve into cooler shades, shadows lengthen, and colors lose their sharpness. A leaf is no longer green, but silver-gray, a path no longer brown, but shadowed with shifting tones. As darkness deepens, the forest is redrawn in a limited palette. Outlines blur, depth vanishes, and what was once familiar becomes strange. A fallen branch looks like the arch of an animal's back. A tangle of roots resembles a figure crouched in wait. The forest, once open and obvious, begins to conceal itself. To walk into the forest at this hour is to step across a threshold. The human body feels the change instinctively. Breath hangs in the cooler air, footsteps sound louder than expected, and the heartbeat seems to echo in one's ears. Even the mind participates. Imagination quickens, inventing shapes and shadows and whispers in the undergrowth. In this way, the transition from day to night is not only an external phenomenon, but an internal one. The forest alters, and so do we. For animals, this hour marks a changing of the guard. Diurnal creatures retreat into shelter, while their nocturnal counterparts prepare to emerge. Deer stand motionless at the edges of clearings, listening, weighing whether to step into the obscurity. An owl shifts on its perch, eyes catching the last light as it surveys the darkness into which it will soon glide. The forest is not quieter, but expectant, like a stage in the pause before the curtain rises. Such moments have long inspired human imagination. In cultures across the world, dusk and nightfall are times when the ordinary order of things seems to loosen. Myths tell of spirits inhabiting fog, of ancestors walking unseen between trees, of hidden presences that grow bold when shadows deepen. Anthropologists note that such beliefs often arise in exactly these sensory conditions, when sight diminishes and sound carries strangely, when the boundary between what is seen and what is imagined becomes thin. In the cool air, the atmosphere itself feels heavier, and with it comes a shift in perception. Humans are diurnal by nature, ill-suited to the dark. In forests, this disadvantage is heightened. Sight is weak, orientation falters, and instinct sharpens in compensation. Every rustle becomes significant, every faint movement a potential sign of presence. It is in this heightened awareness that awe and unease are born. Yet the forest at night is not hostile, only different. What appears mysterious is, to its nocturnal inhabitants, simply the normal order of things. For them, darkness is no veil but a medium as familiar as daylight. To enter this world is to borrow their perspective for a while, to walk in a realm shaped not by light but by shadow, where survival and beauty follow different rules. The silence of the forest falling at dusk is not an ending, but a beginning. It is the moment when one set of voices yields to another, when the visible recedes and the unseen asserts itself. For humans who pause at this threshold, it is an invitation to listen more closely, to see with other senses, to imagine what lies just beyond perception. And so the forest waits, still and shifting, its stories unspoken but ready. The day has withdrawn, the curtain of night has descended, and within it, countless lives are about to unfold. Mist is more than a passing weather phenomenon. It is the breath of the forest itself. Each evening, as temperatures fall and air approaches saturation, invisible vapor condenses into countless droplets suspended in the atmosphere. Together, these droplets scatter light, obscure distance, and wrap the forest in a shifting veil. To the human eye, it is a transformation of aesthetics. To the ecosystem, it is a shift in physics, chemistry, and biology that governs the survival of countless species. Physically, mist forms when relative humidity reaches near 100% and the air can no longer hold its water vapor. In forests, this often occurs during calm nights when daytime heat dissipates and surfaces cool rapidly. The leaves of trees radiate heat into the open sky, cooling faster than the surrounding air. As water vapor condenses on these chilled surfaces, droplets accumulate and are released into the air, blending with ground fog. The result is an environment where visibility shrinks, but moisture availability increases. Unlike rainfall, which arrives in bursts, mist is subtle and continuous, a background supply of water that reshapes forest microclimates. This fine-scale hydration is vital in ecosystems where rainfall is irregular. In temperate, deciduous forests, dew and mist together can contribute several millimeters of effective water input each night during dry seasons. In cloud forests of Central and South America, fog drip, the condensation of mist on leaves that then falls as droplets to the forest floor, can provide up to half of the total annual water budget. Researchers studying these systems emphasize that without this hidden source of moisture, many montane ecosystems would collapse under extended droughts. In an age of climate change, understanding the role of mist has become critical for predicting ecosystem resilience. Mist also alters the forest's chemistry. By coating leaves and bark, it acts as a solvent that dissolves atmospheric particles and nutrients. Nitrogen compounds from lightning, volcanic activity, or even distant industrial sources can attach to mist droplets and be delivered directly to the canopy. This occult deposition, as ecologists call it, supplements rainfall and fertilizes forests in ways often underestimated by traditional models. In some regions, mist contributes more bioavailable nitrogen than precipitation, quietly sustaining the productivity of entire ecosystems. For animals, mist creates an altered sensory world. Visibility drops, shapes blur, and sound is scattered in new ways. Studies show that mist absorbs high-frequency sounds more strongly than clear air, reducing the range of insect and bird calls. Low-frequency sounds, by contrast, travel farther, allowing owls and amphibians to dominate the nocturnal soundscape. Predators that rely on stealth benefit from these conditions, while prey species must adapt with heightened vigilance. The forest in mist is not merely darker, it is acoustically and visually rearranged, a living space reshaped by the condensation of water. Humans, too, respond profoundly to mist. Anthropological research notes that in many cultures, mist is tied to liminality, thresholds between worlds, between known and unknown. Its obscuring qualities foster myths of spirits, ancestors, and hidden realms. Yet beyond myth, there is physiological evidence. Mist increases negative air ion concentrations, which some studies suggest may subtly affect mood and perception, inducing calm or heightened awareness. Whether through science or folklore, mist is recognized as a transformative presence, one that makes the forest feel alive with secrets withheld. Mist does not behave uniformly across a forest. Its density and persistence depend on topography, vegetation, and subtle shifts in air movement. Valleys often trap cool, moist air, allowing fog to linger for hours, while ridges may remain clear under the same conditions. Ecologists studying montane habitats describe this phenomenon as a form of microclimatic zoning. Even within a few hundred meters, some slopes can be perpetually bathed in mist, fostering mosses, lichens, and epiphytes that would not survive in drier microhabitats. These patchy distributions contribute to the mosaic of biodiversity that characterizes complex forests. Epiphytes, plants that grow upon other plants, are among the most visible beneficiaries of mist. In tropical cloud forests, bromeliads and orchids cling to branches high above the ground, relying almost entirely on atmospheric moisture. Their leaves and specialized scales absorb water directly from mist droplets, while their root systems anchor them to bark rather than soil. By creating small reservoirs of water and organic debris, these epiphytes also provide habitat for frogs, insects, and microfauna. In this way, mist does not merely sustain plants, but builds entire microecosystems suspended in the air. Fungi and mosses are equally responsive to mist. Mycologists have long observed that fungal fruiting often coincides with humid nights, when droplets stimulate spore release and growth. Many mosses rely on capillary action to transport water across their surfaces, a process made efficient by the constant supply of fine mist. These organisms thrive where rainfall alone would be insufficient, demonstrating how condensation can rival storms in ecological significance. In boreal and temperate forests, lichens in particular depend on regular mist events. Without them, their growth rates decline sharply, reducing their capacity to serve as bioindicators of air quality. Mist also influences animal behavior in subtle but significant ways. For insects, especially moths and mosquitoes, the presence of fog alters flight dynamics. The tiny droplets increase drag on wings, forcing adjustments in flight paths. Some species reduce their activity, while others exploit the reduced visibility to approach hosts or flowers unnoticed. Amphibians, on the other hand, increase their movement during misty nights. Frogs emerge to feed and breed, their calls carrying farther in the damp air. Salamanders, often limited by desiccation risk, roam more freely when mist saturates the forest floor. For larger mammals, mist can alter patterns of foraging and vigilance. Deer and wild boar are known to move cautiously through dense fog, pausing more frequently to listen for predators. Predators themselves, such as wolves or lynx, may benefit from the cover, using the reduced visibility to stalk prey more closely. Infrared camera studies confirm that hunting success rates for some carnivores rise during foggy nights, underlining how atmospheric moisture directly shapes survival outcomes. Humans observing these dynamics are struck not only by the ecological intricacies, but by the atmosphere of mystery. Writers and poets often describe mist as a veil or curtain, a metaphor rooted in its capacity to obscure and reveal by turns. Modern neuroscience suggests that such metaphors are not accidental. Reduced visibility heightens activity in the brain's prediction centers, compelling us to fill in gaps with imagination. In mist, the forest is never entirely what it seems. It is a shifting puzzle, inviting interpretation while resisting certainty. Climate science has begun to recognize mist not just as a local curiosity, but as a global regulator. In regions where fog is frequent, from the Pacific coasts of California and Chile to the highlands of East Africa, mist sustains forests that, in turn, store vast amounts of carbon. When fog frequency declines, as observed in recent decades along parts of the California coast, tree mortality rises, and ecosystems shift toward drier, less carbon-dense states. Satellite data combined with ground sensors now allow researchers to map these patterns, showing how even subtle changes in fog regimes can cascade through global climate systems. The chemical role of mist also extends beyond nutrients. Mist droplets can scavenge pollutants, removing sulfur compounds, heavy metals, or microplastics from the atmosphere. While this cleansing capacity benefits air quality, it introduces contaminants into forest soils and waterways. Studies in Europe and Asia have documented high concentrations of airborne microplastics within fog droplets, later deposited onto mountain ecosystems. These findings underscore a sobering paradox. The same process that nourishes forests can also deliver the byproducts of human industry, integrating global pollution into the most remote environments. For conservationists, mist is increasingly viewed as a fragile resource. Efforts to restore cloud forests in Costa Rica and Ethiopia emphasize the protection of canopy structure, since tall trees are essential for intercepting fog. Without them, much of the mist passes overhead, reducing water input and biodiversity. Similarly, reforestation projects now consider species selection, not only for soil and climate, but for their ability to capture and distribute atmospheric moisture. Trees with broad, rough leaves are more efficient fog harvesters than smooth-leaved species, altering how regrowing forests interact with mist. Technological innovation has also drawn inspiration from these natural systems. Engineers developing fog nets, mesh structures that capture droplets from the air, often cite the efficiency of forest canopies as a model. In arid regions of Morocco, Chile, and India, fog nets now supply drinking water to communities where rainfall is scarce. These projects highlight how understanding the physics of mist can address human needs while reinforcing the parallels between ecological processes and human survival. Yet beyond science and technology, mist retains its ancient aura of mystery. To walk into a fog-bound forest is to feel boundaries dissolve. Landmarks disappear, distances shrink, and sound becomes both nearer and farther than expected. Philosophers have described mist as an emblem of uncertainty, an environment where knowledge is provisional and perception fluid. In this sense, mist becomes not only an ecological force, but a metaphorical one, teaching humility in the face of what cannot be fully grasped. Ultimately, the breath of mist is the forest's quiet testimony to resilience. It is the gentle balancing of water and air, the veil that both conceals and sustains. In every droplet lies a story of condensation, chemistry, and connection, evidence that life depends as much on subtle, unseen rhythms as on the dramatic events we more easily recognize. To stand in such a forest is to feel the atmosphere itself alive, exhaling and inhaling in tandem with the earth. At night, the forest becomes a reservoir of moisture. The heat of the day has dissipated, and the air, cooling steadily, can no longer hold its burden of vapor. Dew forms on leaves, needles, and soil surfaces, gathering into shining droplets that glisten under moonlight. Though easy to overlook, this nightly cycle of condensation is one of the most important yet underappreciated mechanisms of water delivery in terrestrial ecosystems. Unlike rain, which falls in sudden, measurable bursts, dew and nocturnal moisture accumulate silently and persistently, sustaining organisms that would otherwise suffer from desiccation. Plant physiologists describe dew as a form of occult precipitation, hidden water inputs that supplement rainfall. Measurements across Mediterranean woodlands and temperate forests indicate that dew can account for between 5% and 20% of annual water input. In arid and semi-arid environments, its role is even more pronounced, offering lifelines for shrubs, mosses, and lichens during prolonged dry periods. For the forest, these nightly droplets act as a stabilizer, smoothing the extremes between rainfall events and preventing stress in delicate understory communities. Moisture at night is not limited to dew alone. Soil releases vapor as it cools, while trees themselves redistribute water through hydraulic processes. Some species engage in what ecologists call hydraulic redistribution, moving water from moist, deep soils to drier surface layers via their root systems during the night. This passive flow, driven by gradients in water potential, hydrates shallow roots of neighboring plants, effectively turning large trees into pumps that redistribute underground reserves. In this way, the unseen nocturnal movement of water maintains community resilience, linking species together through shared hydration. For mosses and lichens, nocturnal moisture is often more critical than daytime rainfall. Because these organisms lack true roots, they rely on surface films of water to activate photosynthesis and metabolic processes. Many species are poikilohydric, meaning they can survive complete desiccation, but resume activity within minutes of rehydration. The nightly arrival of dew provides just enough hydration to restart biochemical processes, allowing them to grow in environments where rainfall is sparse. In foggy forests, moss mats on tree trunks capture both mist and dew, creating miniature sponges that sustain insects, microarthropods, and microbial life. Fungi, too, respond to the rhythm of nighttime moisture. Mycologists have documented that spore release in many fungal species peaks during the late evening and early morning hours, coinciding with rising humidity. The sticky surfaces of spores attach more efficiently when coated in moisture, increasing the chances of successful dispersal. Certain wood decay fungi even alter their growth rates in response to humidity changes, accelerating decomposition when surfaces are wet. By timing reproduction and growth to the cycles of nocturnal dampness, fungi weave themselves seamlessly into the forest's hydrological clock. Animals exploit these conditions in diverse ways. Amphibians, with their permeable skin, are perhaps the most obvious beneficiaries. Frogs emerge onto damp leaf litter to feed, while salamanders roam more widely in search of mates. Insects that risk desiccation during hot daylight hours, such as ground beetles and millipedes, take advantage of the cool, wet surfaces to forage safely at night. Even mammals are influenced. Small rodents often time their foraging to coincide with moisture-rich hours when seeds and leaves are softer and easier to consume. The forest at night is not only darker but wetter, reshaping the behaviors of its inhabitants as profoundly as daylight does. The ecological significance of nocturnal moisture extends into the very chemistry of the forest floor. When dew and condensation seep into the litter layer, microbial communities awaken. Bacteria and fungi initiate bursts of activity, breaking down cellulose and lignin into simpler compounds. These processes release carbon dioxide back into the atmosphere, but they also free nitrogen, phosphorus, and micronutrients that enrich the soil. Soil respiration measurements reveal that these nocturnal pulses can represent a significant fraction of daily carbon flux, illustrating how the forest breathes most actively under the cover of darkness. This nightly wetting and drying cycle has consequences for soil stability as well. In semi-arid woodlands, studies show that dew reduces the risk of dust emission by binding fine particles together. In temperate forests, thin films of moisture stabilize the structure of soil aggregates, supporting root growth and microbial habitats. Without these nightly contributions, ecosystems in regions with irregular rainfall would face severe erosion and nutrient loss. Moisture in the dark is more than hydration. It is an architect of soil integrity. Nocturnal water also influences plant physiology beyond hydraulic redistribution. Many trees and shrubs engage in nighttime water uptake through their leaves, a process known as foliar absorption. While often overlooked, experiments using isotopically labeled water have confirmed that leaves can take in dew directly, supplementing root uptake. This strategy is especially advantageous in drought-prone regions or in canopy species exposed to persistent mist. By absorbing water through their leaves, plants bypass the limitations of dry soils and extend their survival window during prolonged dry spells. For grasses, mosses, and lichens, the importance of foliar absorption is even greater. Thin cuticles and high surface area to volume ratios allow them to absorb condensed water efficiently. Some desert mosses, such as Centrichia canenervis, survive almost entirely on dew and fog, entering dormancy during the day and reviving with nighttime moisture. Similar strategies operate in temperate forests, where mosses revive after hours of desiccation, with just a thin sheen of water. These dynamics demonstrate how forest resilience is not tied solely to rainfall, but to a portfolio of subtle water inputs that occur when most observers are asleep. The presence of nighttime moisture also amplifies biogeochemical interactions between plants and fungi. Mycorrhizal networks, already active in exchanging nutrients with their host plants, show heightened transfer rates when humidity is high. Laboratory studies reveal that moisture in the rhizosphere improves fungal conductivity, enabling faster carbon and nutrient flow. This means that dew-laden nights are not just times of hydration, but of accelerated communication and trade between species. Under the cloak of darkness, the forest's underground economy hums at full capacity. Animal behavior reflects these invisible dynamics. Invertebrates, such as snails and slugs, rely on moist conditions for movement, as their locomotion requires a film of water to secrete mucus efficiently. On dry nights, they retreat into sheltered crevices. On damp nights, they emerge in abundance, grazing on algae, fungi, and decaying plant matter. Their feeding accelerates decomposition and nutrient cycling, linking animal activity directly to the presence of dew. Predators respond in turn. Hedgehogs, shrews, and ground beetles increase their foraging when invertebrate activity surges, cascading the effects of nocturnal hydration upward through the food web. The subtle enrichment of moisture at night also shapes forest energy balance. Dew-covered leaves reflect and refract moonlight, creating glints that alter the thermal properties of the canopy. Even small layers of surface water increase emissivity, allowing plants to cool more efficiently by radiating heat to the sky. Thermal imaging studies confirm that dew-laden canopies are several degrees cooler than dry ones, buffering heat stress accumulated during the day. This nocturnal cooling effect is crucial in regions experiencing more frequent heat waves under climate change. The night's water film, though invisible in statistics, is a natural air conditioner for the forest. Climate models increasingly account for these hidden processes. For decades, most global circulation models treated precipitation as rainfall alone. Today, researchers emphasize that occult precipitation, dew, fog, and mist must be included to accurately predict ecosystem function. In arid and montane systems, excluding these sources leads to underestimations of water balance by as much as 30%. Updated models incorporating nocturnal moisture are reshaping our understanding of how forests contribute to regional hydrology and carbon cycles. The message is clear. To understand the forest, one must also understand its nights. Beyond physical processes, nighttime moisture has cultural and symbolic weight. Many traditional agricultural societies, from the Mediterranean to East Asia, celebrated dew as a gift of fertility. Ancient Hebrew poetry described dew as a blessing equal to rain, while in Japanese haiku, the imagery of morning dew embodies transience and renewal. These cultural echoes remind us that humans have long recognized what science is only beginning to quantify: the quiet power of nocturnal water. For conservationists, protecting the cycles of nighttime moisture means protecting forest structure. Canopies intercept mist, while litter layers retain dew. Deforestation interrupts these processes, reducing dew deposition by exposing soil directly to wind and sun. Studies in tropical and temperate systems alike show that deforested areas lose up to 70% of their nocturnal moisture inputs compared to intact forests. This loss exacerbates drought stress, reduces biodiversity, and accelerates soil degradation. Restoring canopy cover and maintaining structural complexity are therefore critical for preserving the silent hydrological services that occur in darkness. Perhaps the most remarkable feature of moisture in the dark is its invisibility to casual observers. Unlike storms, it makes no sound. Unlike rivers, it carves no valleys. Yet its influence permeates every aspect of forest life, from the glistening moss on a tree trunk to the stealth of a salamander, from the respiration of microbes to the cooling of leaves. It is an agent of subtlety, sustaining life through the quiet accumulation of droplets. To grasp its importance is to appreciate that ecosystems depend not only on dramatic events, but also on these understated, recurring gifts. In the stillness of night, the forest is hydrated not by torrents, but by whispers of water. The forest at night is never truly empty. When the sun sets and diurnal creatures withdraw, another cast of characters takes the stage. Their presence is subtle, often betrayed only by glints of eyeshine in the darkness or faint sounds carried on damp air. These are the hunters and wanderers of the shadows: owls, bats, foxes, lynx, and countless smaller species, each finely tuned to thrive in the absence of light. Owls are among the most iconic of these nocturnal predators. Their success lies in an array of specialized adaptations. The structure of their feathers allows for nearly silent flight. Tiny serrations on the leading edges break up turbulence, while velvety surfaces dampen sound. This makes them almost inaudible as they glide through branches. Their eyes, disproportionately large relative to skull size, are packed with rod cells that maximize sensitivity to low light. But it is their hearing that completes the arsenal. Many species possess asymmetrical ear openings, enabling them to pinpoint prey with astonishing precision. Laboratory experiments confirm that barn owls can detect the faint rustle of a mouse beneath a blanket of snow, triangulating sound with a margin of error smaller than a degree. Bats occupy another dimension of the night. Unlike owls, they rely on echolocation, emitting high-frequency calls that bounce off objects and return as echoes. These signals, far above human hearing, construct a three-dimensional map of the environment. Some bats emit over 100 pulses per second during the final approach to prey, adjusting frequency and intensity in milliseconds. Insectivorous bats alone consume millions of tons of insects each year, exerting profound control over ecosystem dynamics. In tropical forests, fruit bats extend their influence further by dispersing seeds and pollinating night-blooming plants, linking their nightly flights to the regeneration of entire habitats. Predators on the ground also exploit the cover of darkness. Foxes, wildcats, and lynx move with caution and patience, blending into the shifting shadows. Their eyeshine, caused by the tapetum lucidum, a reflective layer behind the retina, intensifies their ability to gather light. This adaptation, shared by many nocturnal mammals, doubles the chance of photon capture, enhancing vision under dim conditions. Combined with acute hearing and sensitive whiskers, it allows them to navigate terrain where humans would stumble blind. Camera trap studies across Europe and Asia reveal that lynx and wildcats are most active during moonless nights, when visibility for prey is at its lowest. Not all nocturnal eyes belong to predators. Deer, hares, and other herbivores adjust their routines to forage in darkness, trading visual clarity for reduced exposure to daytime hunters. Their wide-set eyes maximize peripheral vision, while heightened sensitivity to movement helps them detect threats in limited light. These prey species rely on caution, frequent pauses, raised ears, and sudden freezes at the faintest sound. In misty forests, such vigilance becomes even more critical as reduced visibility tilts the balance towards stealthy hunters. The sensory adaptations of nocturnal animals reveal an evolutionary arms race between predator and prey. While owls and bats refine silence and echolocation, rodents and insects develop countermeasures. Many moths, for instance, have evolved ears tuned specifically to detect bat calls. Upon hearing the ultrasonic clicks of an approaching predator, they perform erratic flight maneuvers, sudden dives, spirals, or drops to throw off pursuit. Some species even emit their own ultrasonic clicks, jamming the sonar of their hunters. This dynamic of call and response illustrates how the night is not a static environment, but a battlefield of perception. Rodents, too, have adapted to the demands of the dark. Species such as voles and mice rely heavily on vibrissae, long, sensitive whiskers, to navigate through dense undergrowth. These tactile sensors detect minute air currents and obstacles, providing a spatial awareness that complements limited vision. Their hearing is equally refined, extending into ultrasonic ranges that allow them to communicate with high-pitched squeaks beyond the detection of many predators. Experiments with infrared cameras have shown that rodents adjust their foraging strategies depending on moonlight intensity. They venture farther under new moons and stay closer to cover during bright nights, balancing risk and reward in a shifting lunar landscape. Among the most fascinating nocturnal navigators are amphibians, frogs and toads. Their skin permeable and vulnerable to drying, time their movements to coincide with humidity and darkness. Their eyes, equipped with a reflective tapetum like many mammals, grant them enhanced vision in low light. During breeding seasons, entire wetlands come alive at night with choruses of calls, each species occupying its own acoustic niche to avoid overlap. These vocal displays are not merely for attraction, but also for territory defense, creating a soundscape as complex as the daytime songs of birds. Insects amplify this complexity further. Fireflies, active during the twilight hours, communicate through bioluminescent flashes. Each species has a distinct rhythm and pattern, allowing males and females to identify one another amid a crowded night sky. Some predators exploit this system. Certain species of predatory fireflies mimic the flashes of females to lure unsuspecting males, turning signals of courtship into deadly traps. In this interplay of light and deception, the forest night becomes both stage and arena, where survival depends on deciphering and manipulating signals in darkness. Large mammals demonstrate a different relationship with night. Wolves and wild boar, for instance, use darkness as a cloak to expand their ranges with reduced human disturbance. In many parts of the world, camera trap studies show that mammalian activity is shifting toward nocturnality in response to human presence. This ecological time shift allows animals to avoid encounters with humans, but it also reshapes predator-prey interactions. Deer pursued primarily during the day must now contend with hunters that follow them into the night, altering grazing patterns and migration routes. The modern night forest reflects not only natural evolution, but the growing influence of human activity. For humans, Witnessing these dynamics often comes in glimpses: glowing eyes caught in a flashlight beam, the flutter of wings overhead, or the sudden stillness of prey sensing danger. Yet behind each moment lies a deep web of adaptations, a biological choreography refined over millions of years. In the shadows, survival is not brute force, but fine-tuned sensitivity, where the faintest sound or flicker of movement can mean the difference between life and death. The night forest is also a canvas for cooperation, not just conflict. Many nocturnal animals form subtle alliances that increase their chances of survival. Insectivorous bats, for example, often hunt in loose groups, each individual adjusting its echolocation frequencies to reduce interference with its neighbors. This phenomenon, known as jamming avoidance, ensures that multiple hunters can exploit the same airspace without confusion. Similarly, packs of wolves coordinate through howls and scent trails, synchronizing their movements across large territories. These strategies reveal that communication in the dark is as much about coordination as it is about secrecy. Moonlight adds another layer of complexity. Its waxing and waning alter the behaviors of countless species. Predators like owls often hunt more successfully during brighter nights, when prey animals are more visible against the forest floor. Yet prey species, in turn, become more cautious, restricting movement under full moons to avoid detection. Ecologists call this phenomenon the landscape of fear, where the intensity of lunar light reshapes entire ecosystems. Studies in African savannas and European woodlands alike show measurable declines in herbivore activity during full moons, a pattern mirrored by increases in predator success. The lunar cycle, in this way, becomes a silent conductor of nocturnal life. Technological advances have deepened our understanding of these hidden dramas. Thermal cameras, bioacoustic sensors, and satellite collars now track nocturnal animals with unprecedented detail. These tools reveal patterns invisible to the naked eye: migration routes timed to avoid human settlements, ultrasonic calls exchanged between distant bats, or lynx navigating silently through mist-shrouded valleys. Such data not only illuminate the strategies of individual species, but also show how entire food webs reorganize under the cover of night. Conservationists rely on this knowledge to design corridors, regulate hunting seasons, and mitigate human disturbance, ensuring that the ancient rhythm of night predation endures. Culturally, the glowing eyes of nocturnal animals have long haunted human imagination. Folk tales across continents portray them as omens, harbingers of spirits, demons, or guardians of hidden knowledge. In European traditions, the owl's gaze was seen as both a warning of death and a symbol of wisdom. In many indigenous cultures, eye reflections in the dark embodied ancestral spirits watching over the living. Modern science explains eye shine through physics and anatomy, yet the symbolic power of those glimmers remains undiminished. To meet a pair of glowing eyes in the forest is still to feel the primal tension between curiosity and fear. Ultimately, the eyes in the shadows remind us that the forest at night is not an empty stage, but a thriving realm. Each reflection, each fleeting sound, is evidence of a life adapted to conditions most humans rarely experience. Predators hone silence and perception, prey refine vigilance, and both rely on the subtle interplay of darkness, mist, and moonlight. In these encounters lies the essence of nocturnal ecology, survival shaped not by brute strength, but by finely tuned senses. To step into this world is to recognize that the forest never sleeps, it merely shifts its cast, inviting us to glimpse the actors who emerge when the sun withdraws. When darkness deepens over the forest, silence is never absolute. Instead, it gives way to a chorus, layered, shifting, and rich with meaning. From the rhythmic calls of frogs in wet depressions to the high-pitched stridulations of crickets, the night is alive with sound. These voices, often unnoticed by human ears, dulled by the noise of cities, form one of the most complex acoustic environments on Earth. Scientists refer to this as the biophony of the night, the collective sounds produced by living organisms that fill the auditory space once dominated by daytime birds and insects. In temperate forests, the first performers of the nocturnal symphony are often amphibians. Frogs and toads emerge onto damp soil or perch near water bodies, their vocal sacs inflating into resonant balloons. Each species has its own distinct call, from the deep croaks of bullfrogs to the sharp trills of tree frogs, and these calls rarely overlap by accident. Through evolutionary refinement, amphibians partition the acoustic spectrum, occupying different frequencies, rhythms, or microhabitats to minimize interference. This ensures that each male's call can be heard by potential mates while avoiding confusion with neighbors. In tropical forests, where dozens of species may call simultaneously, the result is an extraordinary layering of sound, a living polyphony shaped by natural selection. Insects soon join this chorus, filling in higher frequencies. Crickets rub their forewings together in stridulation, producing chirps whose pitch is influenced by temperature. Katydids generate louder, more complex calls that carry across understories, while cicadas, in some regions, produce pulsing drones that reverberate through entire valleys. To human perception, these sounds may blend into background noise, but within insect societies they serve critical functions: territory defense, mate attraction, and even species recognition. Recent research using bioacoustic sensors has revealed that many insect calls extend into ultrasonic ranges entirely beyond human hearing, expanding the chorus into hidden registers. Birds are not wholly absent from this nocturnal performance. Nightjars, whippoorwills, and owls contribute distinctive notes. The repeated calls of nightjars resemble incantations, their cryptic plumage allowing them to vanish into branches while they vocalize. Owls, with their hoots and screeches, punctuate the soundscape less frequently, but with commanding presence, their calls serving as both territorial markers and communication between mates. In regions where multiple owl species overlap, call timing and pitch are carefully staggered, a nocturnal counterpart to the dawn chorus sung by their diurnal relatives. The forest's acoustic environment is not shaped solely by biology. The physics of night air amplifies certain sounds and dampens others. Cooler, denser air transmits low frequencies farther, allowing deep frog croaks or owl hoots to travel impressive distances. High-pitched insect chirps, by contrast, attenuate quickly, creating intimate acoustic spaces. Mist and humidity further alter these dynamics, scattering and absorbing sounds, sometimes making distant calls seem close and near ones vanish into haze. For animals, navigating this shifting acoustic landscape requires extraordinary sensitivity. Ears attuned not only to frequency, but to subtle variations in reverberation and distance. The night chorus is more than a collection of isolated voices. It is a dynamic system where species adjust to one another in real time. Acoustic ecologists describe this as niche partitioning, a process where organisms modify their calls to avoid overlap. Frogs may adjust the timing of their croaks, while crickets alter the pitch of their chirps if nearby sounds interfere. In some tropical forests, studies show that dozens of species create a coordinated mosaic of sound, each occupying a unique temporal or frequency window. This fine-tuned arrangement ensures that communication remains effective even in the densest cacophony. Predators exploit this soundscape with equal sophistication. Owls and bats use acoustic cues to detect the location of prey hidden in darkness. A rustle in the leaf litter, the sudden silence of a cricket, or the irregularity of a frog's call may signal an opportunity. For bats in particular, the interplay between their echolocation and the background chorus is complex. While echolocation pulses operate at ultrasonic frequencies, they can still be influenced by the density of lower-frequency calls, forcing bats to adjust their sonar to maintain precision. In this way, the biophony of the night does not merely serve communication, it actively shapes predator-prey interactions. The chorus also acts as an environmental indicator. Because many nocturnal species are sensitive to humidity, temperature, and pollution, changes in their vocal activity provide early warnings of ecosystem stress. In amphibians, declines in calling intensity often precede population collapses linked to habitat loss or disease, such as chytrid fungus infections. Bioacoustic monitoring has become a valuable conservation tool, allowing researchers to track biodiversity without intrusive surveys. Automated sensors record soundscapes continuously, revealing long-term shifts in the abundance and diversity of nocturnal voices. These recordings not only aid science, but also preserve acoustic archives of forests that may one day be silenced by human activity. Human noise increasingly intrudes upon this delicate balance. Highways, logging operations, and urban expansion inject artificial sounds into the night, masking natural calls. This phenomenon, termed acoustic pollution, disrupts communication and reduces reproductive success in species that depend on vocal signals. Frogs calling near busy roads have been observed to increase their volume, a strategy that comes at the cost of energy and increased predation risk. Similarly, owls and nightjars alter their calling patterns in the presence of persistent human noise, with unknown long-term consequences. The intrusion of artificial sound into the nocturnal chorus is one of the subtler but more insidious ways that human activity reshapes ecosystems. Despite these pressures, the night chorus retains an extraordinary capacity for resilience. In some disturbed habitats, species adapt by shifting their acoustic strategies, creating new niches in the soundscape. In urban woodlands, for example, crickets may call at slightly different frequencies than their rural counterparts, exploiting acoustic windows left unfilled by traffic noise. Such flexibility illustrates the evolutionary potential embedded in sound, reminding us that communication is both fragile and adaptable. The voices of the night are not static relics. They are active participants in the ongoing negotiation between life and environment. Beyond survival, the nocturnal chorus plays a role in shaping ecosystems over evolutionary timescales. Species that succeed in securing clear acoustic channels tend to reproduce more effectively, reinforcing traits that refine call structure and timing. This selective pressure explains the incredible diversity of frog songs, insect stridulations, and bird calls that fill the darkness. Each note in the night represents not only an individual's attempt at survival, but also the outcome of millions of years of evolutionary fine-tuning. The soundscape itself is both an artifact of the past and a living force sculpting the future. The chorus also influences human perception of the forest. For travelers, poets, and scientists alike, the layering of sounds evokes both reassurance and unease. On one hand, the steady rhythm of crickets or frogs provides a sense of constancy, a natural lullaby that has soothed listeners for millennia. On the other hand, sudden interruptions, a silence where calls once echoed, or the abrupt screech of an owl, can trigger heightened alertness. Neurological research confirms that humans are deeply attuned to changes in acoustic environments. Our ancestors depended on such sensitivity to detect predators. Even today, spending time in nocturnal forests can reduce stress and improve sleep quality, precisely because the natural soundscape engages deep, ancient pathways in the brain. Technological advances now allow humans to participate in this soundscape in new ways. Sound recorders and bioacoustic software can render the forest's hidden layers audible. Calls outside human hearing ranges, from ultrasonic bat clicks to infrasonic vibrations of certain insects, can be translated into audible frequencies. These tools reveal a universe of communication that once passed unnoticed. Educational projects increasingly use these recordings to teach ecological awareness, immersing people in soundscapes that convey biodiversity more vividly than numbers on a chart ever could. Climate change, however, threatens the integrity of these symphonies. Shifts in temperature and precipitation alter breeding seasons, causing mismatches between calling behavior and resource availability. Some frog species now call earlier in the year, only to encounter unfavorable conditions for tadpole survival. Insects sensitive to humidity may reduce their activity in drier nights, silencing frequencies that once dominated the soundscape. Long-term acoustic monitoring across continents shows clear trends. The nocturnal chorus is changing, both in volume and composition, reflecting the stresses imposed by global environmental change. And yet, resilience persists. New species move into altered habitats, introducing unfamiliar voices. Survivors adapt, modifying call patterns to fit novel conditions. The night chorus evolves as surely as it has always done, a testament to the adaptability of life under shifting skies. To walk into a forest at night is therefore to enter a living archive of resilience, an acoustic library where every chirp, croak, and hoot records the story of adaptation. In this symphony, no single voice dominates for long. Instead, the beauty lies in the collective, the endless interplay of sound and silence where the forest itself seems to sing. Not every creature of the night announces its presence with a call or a flash. Some move quietly, almost invisibly, shaping the forest through slow persistence rather than spectacle. These hidden wanderers, beetles, salamanders, snails, millipedes, and countless other small organisms, may not command the same attention as owls or wolves, but their combined activity sustains the very fabric of nocturnal ecosystems. Among the most active of these are ground beetles, a diverse family of insects adapted to life in the leaf litter. Many are nocturnal predators, using sensitive antennae to detect vibrations from earthworms, larvae, or other invertebrates. Their hardened exoskeletons and strong mandibles make them formidable hunters in miniature, capable of controlling populations that might otherwise surge unchecked. Long-term ecological surveys have shown that ground beetles are essential indicators of forest health. Shifts in their abundance often reflect changes in soil moisture, pollution, or habitat disturbance. Snails and slugs, in contrast, are slow but indispensable players in the nocturnal web. Their reliance on a moist environment confines their activity largely to the night, when dew and humidity prevent desiccation. Moving with deliberate trails of mucus, they graze on algae, fungi, and decaying plant material, accelerating decomposition and nutrient cycling. Some species specialize in consuming tough fungal fruiting bodies, dispersing spores through their digestive systems. Others feed on tender shoots, acting as selective pressures on plant regeneration. Despite their modest size, these mollusks leave ecological footprints far larger than their trails suggest. Salamanders are another quintessential group of hidden wanderers. Found primarily in temperate and boreal forests, they thrive in damp conditions where their permeable skin can remain moist. Unlike frogs, most salamanders are voiceless, their lives unfolding in silence. Yet they are voracious predators, consuming insects, worms, and small arthropods. In North American deciduous forests, the combined biomass of salamanders can exceed that of all the resident birds and mammals combined, underscoring their central role in energy transfer. Because they are sensitive to pollution and microclimate shifts, salamanders are also critical bioindicators, signaling changes in ecosystem integrity long before they are visible in larger fauna. Millipedes and centipedes embody another dimension of nocturnal activity. Millipedes, with their many legs and slow movements, feed primarily on decaying plant matter, grinding tough litter into fragments that microbes can more readily digest. Centipedes, their faster and more predatory relatives, hunt small insects with venomous forcipules, modified front legs that inject toxins. Both groups shape the structure of the soil community, controlling decomposition rates and influencing nutrient availability. Their activity, though unseen, reverberates through the ecosystem, supporting the growth of plants and the survival of higher trophic levels. These small creatures collectively embody the quiet labor of the night. While predators like owls and bats dominate attention, it is the hidden wanderers that maintain continuity in the forest. They recycle nutrients, stabilize soils, and regulate populations of organisms, even smaller than themselves. Without their contributions, the grander spectacles of the nocturnal world would collapse. In the darkness, their anonymity becomes a form of power, sustaining life precisely because it remains unseen. The activity of hidden wanderers reveals how ecosystems rely on the small and uncelebrated, detritivores, organisms that feed on dead organic matter, are particularly active during damp nights. Woodlice, for example, emerge from crevices in rotting logs, their armored bodies glistening with condensation. They consume leaf litter and wood fragments, breaking them down into nutrient-rich pellets that enrich the soil. Without their work, decomposition would slow, and forests would become clogged with undecomposed material. Microbiologists often describe these animals as ecosystem engineers because they transform coarse debris into substrates more easily processed by fungi and bacteria. Ants are another group that rarely rests. While some species retreat into nests at night, many forage actively under cover of darkness. In tropical forests, army ants march in coordinated swarms, flushing insects from the leaf litter and consuming them in vast numbers. Their raids, though destructive to prey, provide opportunities for other animals. Nightbirds, such as antbirds and nightjars, follow the swarms, snapping up fleeing insects. Even in temperate woodlands, nocturnal ant foraging redistributes seeds, fungi, and nutrients across the forest floor. These tiny workers shape patterns of regeneration in ways disproportionate to their size. Spiders, too, thrive in darkness. Orb weavers construct intricate webs each evening, anchoring their silk between branches and shrubs. The moisture-laden air strengthens the stickiness of their strands, increasing their hunting success. By morning, many dismantle their webs, recycling the silk into new structures for the following night. Ground-dwelling species, such as wolf spiders, hunt without webs, relying on stealth and acute night vision. Their reflective eyes shimmer faintly under moonlight, betraying their presence only to those who look closely. Together, spiders exert enormous control over insect populations, silently policing the forest canopy and floor. Beetles extend this silent governance. Dung beetles, for instance, roll and bury animal waste during the night, recycling nutrients and reducing parasite loads for larger mammals. In savannas, their activity is critical for soil fertility, but even in temperate forests, they play a key role in nutrient redistribution. Carrion beetles specialize in decomposing animal remains, often burying small carcasses underground to feed their larvae. By removing carrion quickly, they prevent disease outbreaks and recycle nitrogen and phosphorus back into the soil. Each species, specialized and efficient, contributes to the unseen continuity of forest life. For many of these wanderers, moisture is both invitation and necessity. On dry nights, activity plummets as small-bodied organisms retreat to conserve water. But when dew saturates surfaces, the forest floor comes alive. Infrared and thermal imaging studies reveal surges of movement under such conditions, with invertebrate densities on the surface increasing several-fold compared to dry nights. This synchronization with nocturnal hydration highlights how tightly life is bound to atmospheric rhythms. The hidden wanderers do not merely endure the night, they thrive because of its dampness and silence. In human culture, these small creatures rarely inspire awe. More often they evoke discomfort. The rustle of beetles in leaf litter, the glimmer of a spider's eyes, the trail of a slug across stone. Yet without them, the beauty of forests would erode unseen. Their labor, humble and continuous, anchors the spectacular displays of larger animals. To recognize their role is to expand our idea of what matters in nature, not only the charismatic, but also the countless small agents whose persistence sustains the whole. Science is only beginning to capture the full importance of these nocturnal laborers. Advances in environmental DNA techniques have revealed astonishing diversity in soil and leaf litter communities, much of it composed of species that are rarely observed directly. By analyzing genetic traces in soil samples, researchers have identified thousands of arthropods, nematodes, and microfauna active primarily at night. This hidden biodiversity highlights how much of the forest's functioning is driven by organisms too small or too secretive to enter the human gaze. Every fragment of decaying leaf is a microhabitat, every drop of moisture a world sustaining hundreds of lives. The contributions of hidden wanderers extend upward through trophic levels. By fragmenting organic matter, detritivores accelerate microbial decomposition, enriching soils and fueling plant growth. In turn, healthier plants support herbivores, which sustain predators. This cascading effect means that the quiet work of a snail grazing on a fallen leaf ultimately resonates in the flight of an owl or the howl of a wolf. Ecosystems are built not on grand gestures, but on these incremental, repeated actions, the daily and nightly labors of the small. In their persistence lies the resilience of the forest. Human activities, however, threaten these delicate networks. Pesticide use reduces invertebrate populations with ripple effects on predators and decomposition rates. Soil compaction from logging or heavy machinery destroys the microhabitats that support millipedes, beetles, and salamanders. Light pollution disrupts the activity cycles of many nocturnal invertebrates, reducing their feeding and reproduction. Conservationists warn that focusing only on large, charismatic species overlooks the foundation. Without the hidden wanderers, the forest's structure begins to unravel from below. Efforts to conserve these overlooked species are gaining traction. Habitat restoration projects now incorporate measures to protect soil integrity and moisture cycles. Leaving dead wood on the forest floor provides essential refuge for beetles and fungi, reducing pesticide reliance and promoting biological pest control sustains insect populations while maintaining balance. Even small-scale practices, such as preserving hedgerows or damp leaf litter in managed forests, can provide lifelines for the myriad tiny organisms that thrive in darkness. Culturally, perspectives are beginning to shift. Artists and educators increasingly highlight the unseen majority of forest life, reframing beetles, worms, and fungi as essential architects rather than nuisances. Citizen science projects invite people to survey invertebrates at night, often revealing unexpected beauty in the minute and overlooked. Glowworms illuminating mossy banks, jewel-toned beetles reflecting moonlight, or salamanders emerging in rainstorms offer moments of wonder that bridge scientific insight with emotional connection. In the end, the hidden wanderers embody the essence of the nocturnal forest: persistence, subtlety, and interconnectedness. They remind us that grandeur is not always loud or visible. Sometimes it is the slow crawl of a millipede, the silent glide of a salamander, or the delicate grazing of a snail on a fungus that holds the forest together. To honor them is to recognize that ecosystems are sustained as much by the unseen as by the spectacular, and that in darkness, life is busiest precisely where our eyes fail to follow. When night falls over the forest, the focus often shifts to animals, while plants are imagined as passive scenery. Yet the botanical world is far from still. Darkness does not halt plant life, it redirects it. Beneath the silence of folded leaves and unmoving stems, complex physiological processes unfold that are critical for survival. Plants breathe, redistribute water, adjust their cellular machinery, and in some cases even open their flowers under the cover of night. Photosynthesis ceases once sunlight disappears, but respiration continues. During the day, plants absorb carbon dioxide and release oxygen while storing sugars. At night, this balance reverses. Mitochondria in plant cells break down sugars to generate ATP, releasing carbon dioxide. Though this process is quieter and less visible than photosynthesis, it is vital. Respiration fuels cellular repair, growth of roots, and the maintenance of living tissues. Without the nightly cycle of energy release, plants could not sustain the activity required when daylight returns. Water relations also change profoundly in darkness. Many plants close their stomata, the small pores on leaf surfaces, to conserve water, reducing transpiration losses. Yet not all follow this pattern. Certain species, particularly those in arid environments, use a strategy known as CAM, crassulacean acid metabolism, photosynthesis. These plants, including cacti and some orchids, open their stomata at night to absorb carbon dioxide when evaporation risk is lowest. The gas is stored as malic acid and later used during the day for photosynthesis. This nocturnal rhythm allows them to thrive in environments where daytime gas exchange would mean lethal water loss. In forests, nighttime moisture offers additional opportunities. Dew and fog can hydrate leaves directly, a phenomenon known as foliar water uptake. Lichens and epiphytes rely heavily on this process, but even trees such as redwoods and beeches have been shown to absorb water through their leaves. This hidden source of hydration supports physiological activity and can mitigate drought stress. Night, far from being a dormant interval, becomes a time when plants quietly drink from the air itself. Floral biology provides some of the most striking examples of nocturnal adaptation. Certain flowers bloom exclusively at night, their pale petals and strong scents designed to attract nighttime pollinators. Jasmine, evening primrose, and several species of orchids unfold after sunset, releasing aromatic compounds that travel farther in cool, humid air. In tropical forests, giant night-blooming cacti open massive blossoms that attract bats and moths. These short-lived flowers concentrate their reproductive energy into a single night, ensuring that pollination occurs under optimal conditions. The forest, therefore, is not only a stage for animal actors at night, but also for plants that time their most critical displays to darkness. Night-blooming plants illustrate how tightly evolution interweaves flora and fauna. Their traits are shaped not only by the absence of light, but by the behavior of nocturnal pollinators. Pale-colored petals are more visible under moonlight, and many flowers release volatile, organic compounds only after sunset. These chemicals create scent plumes that moths and bats can detect from considerable distances. Research in tropical ecosystems shows that nectar production in night-blooming species often peaks during evening hours, synchronizing rewards with the activity of pollinators. Such timing maximizes reproductive success while minimizing competition with day-active species. The forest understory, where light levels are low even at midday, reveals another layer of adaptation. Many shade-tolerant plants maintain photosynthetic machinery tuned to low light, enabling them to capture scarce photons efficiently. At night, these plants enter periods of energy conservation, reallocating resources to root growth or the repair of damaged tissues. Studies using chlorophyll fluorescence imaging have revealed bursts of cellular activity in leaves hours after sunset, suggesting that repair of photosystem components is concentrated in darkness. Without these nightly recovery phases, photosynthetic efficiency would decline rapidly under daytime stress. Seeds and spores also respond to nocturnal cues. Germination in many species is inhibited or stimulated by darkness, depending on ecological context. Small seeded plants that germinate near the surface often require light as a signal of proximity to open ground. Others, particularly in forest understories, respond positively to extended darkness, which indicates burial beneath leaf litter where moisture is stable. These processes show how night influences not only adult plants, but also the earliest stages of life. Circadian rhythms, internal biological clocks, orchestrate much of this nocturnal activity. Plants possess genetic mechanisms that anticipate the cycle of day and night, regulating processes from stomatal opening to hormone production. Even in constant darkness, these rhythms persist for days, underscoring their evolutionary importance. At night, circadian control shifts metabolism towards starch breakdown, providing a steady energy supply until sunrise. This balance is delicate. If reserves are consumed too quickly, plants risk starvation before morning. Too slowly, and growth potential is wasted. The precision of these nightly calculations is a quiet marvel of plant physiology. Interactions with fungi further illustrate the significance of darkness. Mycorrhizal networks often increase activity at night when host plants transfer sugars generated during the day into fungal hyphae. In exchange, fungi deliver water and nutrients back to the plant, processes enhanced by the elevated humidity of nighttime soils. Research has shown that carbon allocation from trees to mycorrhizal fungi peaks during evening hours, suggesting that the hidden economy of the forest is busiest precisely when the canopy appears still. These nocturnal exchanges underpin not only plant survival, but the entire nutrient web of the forest. While many processes at night remain hidden, new technologies are revealing the extent of plant activity in darkness. Infrared gas analyzers, for instance, have shown that nighttime respiration accounts for nearly half of the daily carbon flux in some forests. This means that what seems like a period of rest is actually a major driver of ecosystem metabolism. Thermal cameras have recorded subtle temperature changes in leaves linked to transpiration pulses at night, particularly in species that keep stomata partially open. These findings challenge the old assumption that plants are largely inactive once the sun disappears. Nocturnal plant behaviors also interact with larger climatic cycles. In tropical cloud forests, foliar water uptake from mist contributes significantly to plant water balance. Redwood trees along the California coast are another striking example. Studies reveal that they can absorb up to 40% of their daily water needs directly from fog. At night, when fog is most persistent, this uptake sustains growth and reduces drought stress. With climate change altering fog regimes worldwide, understanding these nighttime dynamics has become essential for predicting forest resilience. The cultural dimension of plants in darkness is equally rich. For centuries, humans have associated night-blooming plants with mystery and symbolism. The evening primrose, opening its blossoms as twilight deepens, has been linked with themes of transience and renewal. Night-blooming jasmine perfumes gardens across continents, evoking romance and serenity. In Mesoamerican traditions, giant moonflowers were revered for their dramatic nocturnal blooms, often tied to lunar rituals. These associations reflect an intuitive recognition that darkness is not absence but transformation, a time when life reveals aspects hidden by daylight. conservation efforts increasingly highlight the need to protect nocturnal ecological interactions. Artificial light at night disrupts many of the processes plants depend on. Streetlights near forests can interfere with flowering schedules, pollinator visitation, and circadian rhythms. Experiments have shown that even low levels of artificial illumination reduce the frequency of moth visits to night-blooming flowers, leading to measurable declines in seed set. As human expansion continues, mitigating light pollution becomes critical not only for animals, but also for the silent, overlooked world of plants in darkness. Ultimately, the nocturnal lives of plants underscore a broader truth. Ecosystems never sleep. Forests breathe, grow, and interact continuously, weaving cycles of carbon, water, and energy through every hour of the day. To witness a flower unfurl at night, to see dew absorbed by moss, or to understand that a tree quietly shares its sugars with fungal partners after sunset is to recognize the ceaseless continuity of life. In the stillness of darkness, the forest does not rest. It transforms, sustaining itself through rhythms both visible and hidden. In the darkness of the forest, when sight is limited and sound distorted by mist, smell becomes one of the most powerful channels of communication. Invisible and often overlooked, scents carry messages across species, linking plants, animals, and even microbes into networks of information. For nocturnal life, odor is not a faint background quality. It is a primary language, as vital as vision in daylight. The physical properties of night enhance this olfactory world. Cool, humid air holds scent molecules longer and carries them farther than hot, dry air. Dew and mist reduce turbulence, allowing chemical signals to linger close to the ground or drift slowly through understories. Predators and prey, flowers and pollinators, even fungi releasing spores rely on these conditions to make themselves known. A molecule of jasmine released at dusk may travel meters farther under calm night air than under the dispersive conditions of midday heat. Plants have long exploited this physics. Night-blooming species produce some of the strongest floral scents in nature, timed to coincide with the activity of moths and bats. These fragrances are complex mixtures of volatile, organic compounds, benzenoids, terpenes, and phenylpropanoids that interact with specialized receptors in pollinators' antennae. Each flower species has a signature scent fingerprint, unique enough for insects to distinguish among dozens of options in a crowded forest. Research has shown that moths can detect certain compounds at concentrations as low as a few parts per trillion, highlighting the extraordinary sensitivity of their olfactory systems. For animals, smell is equally indispensable in navigating the nocturnal forest. Mammals such as foxes, wild boar, and deer rely on scent trails to locate food and assess the presence of rivals or predators. The moist forest floor amplifies these signals, holding on to the chemical residues left by urine, feces, or glandular secretions. Wolves and other carnivores patrol territories by marking them with scent, creating chemical boundaries that remain legible for days. To prey species, these cues are warnings. To members of the same pack, they are maps of ownership and cooperation. Invertebrates also weave themselves into this olfactory conversation. Ants navigate primarily through pheromone trails, which at night persist longer due to reduced evaporation. Colonies exploit these pathways to coordinate mass foraging raids, carrying information about food location and quality. Termites use similar chemical signals to maintain cohesion in their hidden networks. Even fireflies, better known for their light displays, supplement visual communication with pheromones that reinforce mate recognition in the obscurity of dense vegetation. Humans, though less reliant on smell than many forest dwellers, are not immune to its influence. Studies in environmental psychology show that natural scents can evoke strong emotional responses, from calm induced by woody aromas to alertness triggered by the sharpness of resinous compounds. Folklore often reflects this connection. The fragrance of night-blooming jasmine or datura has been linked to enchantment, danger, or divine presence across cultures. In walking through a forest at night, people encounter not only shadows and sounds, but an invisible tapestry of odors that shapes their perception in profound ways. Predators are among the most skilled interpreters of nocturnal scent. Carnivores, such as lynx, wolves, and martens, rely on their acute olfactory senses to detect prey hidden in dense vegetation or underground burrows. A single whiff of volatile compounds released by stressed plants or the faint ammonia of rodent urine can reveal the presence of food meters away. Scientific studies using tracking dogs as proxies have confirmed that scent trails can persist for hours under cool, humid nighttime conditions, providing predators with reliable cues in the absence of vision. This reliance on smell explains why many nocturnal hunters possess enlarged olfactory bulbs relative to their brain size, anatomy finely tuned for the dark. Prey species, in turn, use odor to avoid danger. Deer are able to detect predator scent marks and adjust their foraging routes accordingly. Rodents exposed to the smell of fox urine show elevated stress hormone levels, even without direct predator contact. This chemical awareness allows prey animals to read the landscape of fear through scent alone, modifying their behavior before threats become visible. For smaller organisms, such as insects, olfactory vigilance can mean survival. Many moths are repelled by bat-associated odors, reducing their risk of predation when acoustic detection fails. Fungi add yet another dimension to the olfactory web. Many species release strong, distinctive odors when sporulating, from the earthy smell of truffles to the sharp notes of stinkhorn fungi, which mimic the scent of carrion. These odors are not incidental byproducts, they are strategies for dispersal. Stinkhorns attract flies, which carry spores to new substrates, while truffles emit scents that lure mammals to dig them up, ensuring their spores are spread through digestion. The humid air of the night amplifies these chemical ploys, making fungi as much participants in the olfactory dialogue as animals or plants. Chemical communication also governs reproduction. Many insects release reproductive pheromones at night when cooler conditions extend their persistence. Female moths perch quietly, emitting plumes of pheromones detectable by males kilometers away. Male beetles and cockroaches engage in similar signaling, their antennae designed as highly sensitive receivers. In mammals, pheromones influence everything from mate choice to maternal bonding. Female mice and estrus release specific compounds that guide males directly to them, while mother-infant recognition in ungulates relies heavily on scent. These nightly chemical exchanges ensure that reproduction proceeds even in near total darkness. Humans have long tapped into this hidden world, often unknowingly. The use of resins, incense, and aromatic plants in rituals across cultures reflects an intuitive recognition of the power of scent. Many traditions consider the forest at night to be a sacred space precisely because of its intoxicating smells: damp soil, blooming flowers, fungal, fruiting bodies. Modern science is now beginning to confirm what folklore suggested. Exposure to natural forest odors can influence human physiology, reducing stress hormones and improving mood. The nocturnal forest is not only a place of sound and sight, but an enveloping olfactory experience that shapes behavior across species. The ecological importance of nocturnal scent is increasingly recognized in conservation science. Artificial light at night not only disrupts visual and acoustic behaviors, but also alters chemical signaling. Studies show that many nocturnal pollinators reduce their visits to night-blooming flowers under illuminated conditions, not just because of light distraction, but because scents disperse differently in disturbed microclimates. Warmer air near streetlights accelerates the breakdown of volatile compounds, shortening the range of floral plumes. In this way, light pollution silences not only the chorus of the night, but also its language of smell. Climate change exerts another layer of influence. Rising temperatures and shifts in humidity alter how far and how long scent molecules can travel. Drought-stressed plants often release different blends of volatiles, which can confuse pollinators accustomed to stable chemical fingerprints. Insect declines linked to climate change further compound this problem, as fewer pollinators remain to interpret floral signals. Researchers warn that the breakdown of these chemical communications could destabilize plant reproduction and, by extension, entire food webs dependent on fruits and seeds. Yet resilience remains part of the story. Some plants and animals demonstrate remarkable flexibility in their chemical signaling. Certain moth-pollinated flowers have been observed to shift the timing of scent release, compensating for altered pollinator activity. Mammals adjust by expanding the range of scent marking or changing the compounds they emphasize. Even fungi exhibit adaptability, with some species modifying their odor profiles in response to shifts in humidity or microbial competition. These adjustments illustrate that the olfactory language of the night, though fragile, is also dynamic and capable of evolution. For humans, acknowledging this hidden language opens doors to new perspectives on forest ecology. Biologists are beginning to frame ecosystems not only in terms of energy and nutrient cycles, but also as networks of information where chemical cues act as messages shaping behavior. This recognition has inspired biomimetic technologies, from scent-based pest management in agriculture to olfactory sensors modeled after moth antennae. By decoding how the forest speaks in scent, humans are learning to listen to an ancient communication system that predates speech and song. Ultimately, the language of smell reveals that the nocturnal forest is alive with dialogue we rarely perceive. Every drifting plume of jasmine, every trace of musk on a trail, every earthy note of fungi carries meaning. To other species, these odors are not background ambience, but essential guides for survival, reproduction, and cooperation. For us, they are reminders that the forest speaks in many tongues, not only through sight and sound, but through invisible molecules on the night air. To walk among them is to enter a conversation millions of years in the making, one that continues every evening as shadows deepen and the unseen symphony begins anew. At night, the towering trees of the forest, the silent giants, shift from their daytime spectacle of photosynthesis to quieter but equally vital processes. Respiration continues in the dark. The sugars created during the day are broken down, releasing carbon dioxide and fueling the metabolic maintenance of tissues. A single mature oak may release tens of liters of CO2 each hour through this process. A reminder that trees do not sleep but operate continuously, balancing global carbon cycles across the circadian rhythm. Studies now confirm that respiration rates rise with warmer nights, linking climate change directly to forest carbon dynamics. Water, too, flows in complex patterns long after the sun has set. Nocturnal transpiration, the release of water vapor through stomata that never close entirely, was once thought negligible. Yet evidence shows it can reach 10 to 15% of daily water loss in humid regions, subtly humidifying the understory and altering local microclimates. In drier landscapes, trees sharply reduce this flow, showing a finely tuned sensitivity to resource conservation. Perhaps most striking is hydraulic redistribution. Deep-rooted species such as oaks, beeches, or eucalypts draw water upward from moist layers deep underground and leak it into drier soils closer to the surface. This passive pumping occurs most strongly at night when transpiration is low. The redistributed water supports neighboring plants, grasses, shrubs, and seedlings, effectively stabilizing entire plant communities during drought. Fieldwork in African savannas and North American woodlands demonstrates that this phenomenon increases ecosystem resilience as heat waves and dry spells become more frequent. Trees also shape the ecology of their immediate surfaces. Bark crevices host beetles, spiders, and resting moths. Cavities provide shelter for bats and owls. Mosses and lichens trap dew, channeling droplets back to soil organisms. In these quiet interactions, giants are not inert structures, but scaffolds for life, distributing energy and matter vertically across forest strata. Cultural narratives echo these ecological truths. Myths across continents portray trees as guardians of thresholds, rooted in soil, yet rising into sky. To walk among them at night is to sense their duality, permanence in their centuries of growth, impermanence in their constant physiological flux. Science now affirms what traditions intuited, that giants embody continuity, sustaining life hour by hour, even in darkness. Beyond their internal physiology, trees at night sculpt the sensory and chemical environments of forests. Their trunks and crowns dictate how sound travels and how shadows fall. Owls perch silently on branches, launching into moonlit clearings. Bats thread between canopy corridors, their echolocation bouncing differently off leaves, gaps, or bark. Mammals, such as deer and wild boar, navigate under cover, relying on the concealment that tree density provides. The structure of trees defines how nocturnal life perceives and survives. Trees continue releasing volatile organic compounds, VOCs, even at night. These chemical signals attract pollinators of night-blooming flowers, deter herbivores, and influence atmospheric chemistry. Some volatile organic compounds contribute to the formation of aerosols that seed cloud condensation, linking forest giants to weather systems far beyond their crowns. Roots, meanwhile, pulse with nightly activity. Carbon fixed in daylight flows downward to fuel root growth and exudates that sustain microbial life. Mycorrhizal fungi extend these networks outward, exchanging nutrients between species and allowing carbon to move between individuals. Isotopic tracer studies reveal that this carbon sharing peaks at night, underscoring that even giants depend on unseen collaborations beneath the soil. Technological advances now illuminate subtle nighttime rhythms. High-resolution dendrometers reveal that trunks shrink slightly at night as elastic tissues release stored water, re-expanding with morning transpiration. This daily pulse acts like a heartbeat, synchronizing trees with the forest hydrological cycle. Though imperceptible to human senses, such oscillations highlight the dynamism hidden in apparent stillness. Old-growth giants carried these processes across centuries. Redwoods, sequoias, and baobabs, some millennia old, embody resilience yet remain vulnerable. Logging, disease, and climate extremes erode populations. Warming nights intensify respiration, while droughts weaken hydraulic redistribution. Artificial light alters insect and bat behavior in canopies, disrupting pollination of night-blooming plants. Conservationists stress that losing giants means losing functions that cannot quickly be replaced by younger trees. Human culture has long mirrored these scientific insights. Druids honored oaks as keepers of wisdom. East Asian traditions imagined spirits dwelling within trunks. Today, forest therapy practices affirm the restorative presence of giants. Time spent among them at night reduces stress, echoing the calm power that ecosystems themselves rely upon. If trunks anchor ecosystems, the canopy connects them to the cosmos. Leaves and branches form a living ceiling that filters moonlight and starlight, modulating how nocturnal life experiences the sky. Moonlight falling through foliage creates mosaics of brightness and shadow that alter predator-prey interactions. Owls hunt more effectively on bright nights, while small mammals retreat into cover until lunar intensity wanes. Stars, though faint through foliage, serve as navigation beacons for migrating birds and insects, guiding movement through forest corridors. The canopy also shapes microclimates under celestial influence. On clear nights, leaves radiate heat into the sky, cooling rapidly and fostering dew formation. Epiphytes, lichens, and mosses harvest this water, while droplets drip to lower strata, feeding soil organisms. In cloud forests, canopies intercept fog and mist, delivering occult precipitation that can match or exceed rainfall as a water source. These processes link the forest hydrological cycle directly to sky conditions. Yet modern intrusions alter this delicate dialogue. Artificial light at night spills from cities and farms, dulling contrasts between stars and darkness. Migratory birds become disoriented, circling lit areas until exhaustion. Fireflies vanish from forest edges overwhelmed by stray light. The canopy, once mediator between cosmos and forest, now reflects human glow, severing ecological connections honed over millennia. Still, cultural traditions remind us of the canopy's symbolic role as a veil between worlds. Indigenous cosmologies often describe ancestors shining through treetops. Polynesian navigators used stars framed by foliage as waypoints. In European folklore, moonbeams piercing branches marked gateways between realms. Modern science validates these intuitions. Canopy structure indeed filters and frames celestial light in ways crucial to life. Technologies such as drones and spectroradiometers now quantify this filtering, showing how small canopy gaps amplify starlight, while dense foliage reduces illumination by over 90%. For animals with sensitive vision, moths, owls, and small mammals, these gradients shape behavior. To humans, the view of constellations through branches evokes awe, linking earthbound ecosystems with cosmic immensity. Ultimately, the giants and their canopy embody endurance and connection. Their trunks anchor networks of soil and water. Their crowns converse with stars and moon. At night, they do not rest but pulse with hidden flows, host myriad lives, and mediate between terrestrial and celestial realms. To stand beneath them is to witness power expressed not in spectacle, but in continuity, the forest's silent dialogue with both earth and sky. The history of humans and forests begins deep in time, when the first hominins lived along woodland edges in Africa. Forests offered fruits, roots, game, shelter from wind, and protection from predators. Traces of microscopic wood fibers on prehistoric stone tools reveal that trees were among the earliest materials shaped by human hands. In the glow of firelight reflecting on bark, the forest was not simply backdrop. It was shelter, resource, and companion. As glaciers retreated at the end of the last ice age, new birch and pine forests expanded across Europe and Asia. Human groups followed, settling where the canopy offered food and refuge. Ancient soils layered with charcoal show how people used fire not only for warmth, but to manage landscapes, opening glades for grazing animals, encouraging certain plants, and preparing ground for early cultivation. In Asia, bamboo, rice, and tea were integrated with woodland margins, an early form of agroforestry that shaped both ecosystems and cultures. Elsewhere, people coppiced saplings, bent green wood for frames, and carved dugout canoes that stitched river and forest into one corridor. Forests entered human imagination as well as daily survival. Mesopotamian myths describe the cedar forest as a threshold between worlds, sacred and dangerous. In Europe, oak groves became ritual centers where trees embodied ancestors and spirits. Even words reflect reverence. Silva in Latin, Wald in Old High German, Nemeton in Celtic traditions, each carrying connotations of mystery, depth, and belonging. The relationship was never one of simple extraction. Fire, while clearing, also sustained open woodlands rich in biodiversity. Seeds carried in baskets or caught on clothing expanded the range of fruit-bearing trees. Selective cutting of branches and trunks allowed regrowth, maintaining a living resource. Forest and human were co-creators, each shaping the other's future in subtle, enduring ways. Knowledge moved with people, how to read bark for water, how to follow bird calls to fruiting trees, how to step lightly where roots breathe. Even toolkits evolved with the forest, scrapers for fibers, adzes for shaping beams, cords from bast that held shelters against the wind. Night amplified this kinship. Fire rings pushed back darkness, just enough to work and to listen. In the hush, senses widened. The click of beetles, the soft wing beat of an owl, the faint drip of mist from moss. Such cues meant safety, food, and orientation. Over generations, they also became story. To walk beneath trees at night today is to feel those echoes. Shadows cast by moonlight recall both the comfort and the uncertainty of early life. The rustle of leaves carries memory, the forest as origin, companion, and first teacher. Under that canopy, humans learned patience, timing, and reciprocity, taking while tending, moving while returning. The path out of prehistory was traced along tree lines. Even as fields and towns emerged, the cadence of forests remained within us, a quiet metronome guiding work, rest, and wonder. That is why, even now, a night forest feels familiar. It speaks to skills and stories written into our nervous system. With the rise of civilizations, forests became the foundation of expansion. Bronze smelting required vast amounts of charcoal. Entire oak and pine groves fell to meet demand. Timber was transformed into ships, temples, and city walls. By 1000 CE, much of the Mediterranean's ancient cover was gone. Its trunks turned into fleets that carried trade and conquest across seas. Forests were also common ground. In medieval Europe, peasants relied on forest commons for firewood, herbs, and grazing. These lands sustained local communities and acted as social equalizers. In Japan, sacred groves around Shinto shrines preserved biodiversity precisely because they were culturally protected. In the Amazon, indigenous peoples enriched soils with terra preta, dark earth enriched by charcoal and organic matter, which still nurtures thriving forests centuries later. Elsewhere, coppicing and pollarding allowed repeated harvests without destroying trees, showing an early grasp of sustainability. Science, too, took root in forests. Carl Linnaeus built his plant classification system by studying Swedish woodlands. Alexander von Humboldt, wandering through South American jungles, described the vertical layering of forests, shaping modern ecology. Today, dendrochronologists read tree rings as living archives of droughts, volcanic winters, and atmospheric changes, linking human history to the testimony of trunks. Even early medicine emerged from bark and leaf, willow yielding salicin, precursor to aspirin, and cinchona, providing quinine to treat malaria. Forest knowledge traveled with empires, sometimes as healing, sometimes as exploitation. But progress came at a cost. The Industrial Revolution devoured wood and coal, filling skies over London and Paris with smoke. Expanding railroads demanded sleepers cut from forests across continents. Colonial markets extracted tropical hardwoods, stripping landscapes and erasing local stewardship. By the 20th century, scientists warned that unchecked deforestation threatened not only wildlife but human survival itself. And yet forests remained symbols. German Romantic poets celebrated the wald as essence of identity. Russian birch groves became emblems of resilience. American thinkers like Thoreau and Muir saw forests as sanctuaries, helping to ignite conservation movements. The forest was never reduced entirely to timber. It remained a mirror in which humanity confronted ambition, loss, and the longing for renewal. At night, among the trees, one senses this weight of history. The quiet trunks are reminders of both civilization's foundation and the scars of overreach. Forests have built cities and ships, but they also whisper of limits, teaching humility beneath their canopies. To pause under their branches is to encounter a record of choices, what was taken, what was preserved, and what still waits for care. Mist has always held a special place in the human imagination. especially when it drifts through forests. Scientifically, it is condensation, tiny droplets of water suspended in the air, clinging to branches, moss, and needles. For ecosystems, it is a resource. From California's redwoods to the Andean cloud forests, up to a third of the water input may come from fog and occult precipitation. Yet for humans, mist was never only moisture. It blurred outlines, erased paths, and suggested that something hidden might be moving between the trunks. Across myths, the mist-shrouded forest often appears as a threshold. In Celtic traditions, fog was seen as the veil between the living world and the other world. Germanic tales speak of dark forests where drifting mists took the shapes of ancestors or wandering spirits. In Japan, forests and mist converge in the idea of yurei, restless souls in white, drifting just above the ground. The shadowed forest, deepened by mist, became an image of what lies beyond sight, a place where the known world thins. Shadows themselves carried symbolic weight. Anthropologists note that in many cultures, the shadow was thought to be part of the soul. In a moonlit forest, human shadows merged with those of branches, creating figures that seemed half human, half tree. Among the Maya, the play of shadows under lunar light was read as a sign from the gods, while in Scandinavian folklore, beings without shadows were omens of misfortune. Science today describes these patterns as the filtering of light through shifting leaves, but myths cast them as signs of presence or danger. Modern psychology helps explain why such impressions are so powerful. Mist reduces visibility, heightens attention to sound and movement, and triggers vigilance. In nocturnal forests, heart rate and stress responses are measurably altered, a survival legacy from ancestors who could not know whether danger or safety was hidden in the fog. Biology, culture, and myth entwine. Mist as water source, as psychological force, and as symbol of transition. Today, forests cover about 31% of Earth's land and host more than 80% of terrestrial biodiversity. They store around 650 gigatons of carbon, more than all known fossil fuel reserves combined. Yet satellites reveal how fragile this cover has become. In 2023, the Amazon lost over 10,000 square kilometers of forest, while boreal regions faced record-breaking fire seasons. These changes reverberate far beyond their borders, altering rainfall patterns, air quality, and global climate. Still, renewal is possible. Reforestation projects in Europe and Asia expand green cover. On China's Loess Plateau, barren soils have been transformed into woodlands that stabilize erosion and harvest water from mist. In cities worldwide, urban forestry grows. Tree-lined boulevards, cool heat islands, filter air, and offer psychological relief to millions. Forests are no longer confined to wilderness. They are woven into the design of resilience. Science reveals new layers of connection. The discovery of the wood wide web, fungal networks linking roots, shows how trees exchange nutrients and carbon, strengthening communities through cooperation. Old-growth giants redistribute water at night, sustaining seedlings through drought. Forests are not solitary collections of trees, but interconnected systems, whispering in flows of carbon, water, and information. Even death is part of the cycle. Fallen logs host fungi, insects, and seedlings, turning loss into renewal. Culturally, forests remain sanctuaries. Practices like Japan's Shinrin-yoku, forest bathing, and European forest therapy highlight their restorative power. Clinical studies confirm what poets long intuited: time under canopies lowers stress hormones and blood pressure. At night, this effect deepens. Moonlight filtering through leaves, stars glimpsed through gaps, create atmospheres of calm that remind us survival is also spiritual. In literature and film, forests still embody both refuge and mystery, echoing their ancient symbolic role. The future is uncertain. Climate extremes push species beyond tolerance. Invasive pests spread through trade. Logging and agriculture still advance. Yet technology, from satellite monitoring to genetic conservation, offers tools for stewardship. Ultimately, the outcome depends less on tools than on will. Whether humans can see forests not as commodities, but as companions. To stand in a night forest is to feel this continuum, the memory of origins, the foundation of civilizations, the challenge of tomorrow. The silent giants remain, waiting to be partners still if we allow them. Before sunrise, the forest enters its most delicate threshold. The long hours of darkness begin to dissolve, yet the sun has not yet breached the horizon. This liminal phase, the dawn's first veil, is neither night nor day, but a convergence of both. Mist often thickens in these moments, condensing out of cooling air as temperatures reach their lowest point. The forest, saturated from the night's breath, seems to hold itself in suspension, waiting for light to return. For nocturnal animals, this time is both opportunity and urgency. Predators extend their final hunts, knowing the cover of darkness is fading. Owls deliver last strikes against distracted rodents, while bats sweep low over clearings in search of insects before retreating to roosts. Foxes and wolves move quickly back toward dens, carrying the spoils of the night. Each action is sharpened by the awareness that visibility will soon expand, exposing them to new risks and altering the balance of their world. Diurnal animals, meanwhile, begin their stirrings. Songbirds test their voices in the growing half-light, establishing territories and greeting mates. This dawn chorus is one of the most studied acoustic events in ecology, remarkable for its consistency across habitats. Birds exploit the acoustics of pre-dawn air, which carry sound farther, allowing calls to reach maximum range. The overlap of nocturnal silence giving way to diurnal song creates a unique auditory blend, the fading of owls punctuated by the rise of robins, thrushes, and warblers. The forest shifts from whispers to declarations, announcing the transition in sound before light fully confirms it. Plants, too, respond to this threshold. Stomata begin to open in anticipation of photosynthesis, guided not only by light but by circadian rhythms that predict dawn. Leaves adjust their angles, orienting themselves for optimal capture of the first photons. In many species, floral scents diminish as daylight approaches, conserving resources once pollinators of the night retreat. Conversely, day-blooming flowers prepare to unfurl, releasing new scent blends that attract bees and butterflies. This precise choreography ensures that resources are not wasted, aligning plant metabolism with the rhythms of pollinators and the sun. Mist and dew shape these early hours in profound ways. As droplets evaporate under the first warmth of sunlight, They release nutrients captured overnight, nitrogen, sulfur, and organic particles absorbed from the atmosphere. This occult deposition fertilizes leaves and soils, delivering subtle but essential enrichment. For insects emerging in dawn's cool, wet air, this transition can be perilous. Wings heavy with dew delay flight, making them easy prey for birds taking advantage of slowed movements. Predation rates often peak at dawn, reflecting both the vulnerability of nocturnal species winding down and the eagerness of diurnal species beginning anew. The first veil of dawn is also a time of dramatic atmospheric change. As the sky lightens, temperature inversions that held mist close to the ground begin to break. Air currents stir, dispersing fog into wisps that drift upward through the canopy. This transition alters sensory conditions across the forest. Scents carried richly in still, damp air are suddenly diluted. Acoustic clarity shifts as turbulence increases, changing how far sounds can travel. For animals, the rules of perception are rewritten within minutes, demanding rapid adjustments. Predators and prey alike are attuned to these cues. Studies of small mammal behavior reveal that rodents increase their speed and alertness during dawn transitions, compensating for the loss of fog's concealment. Birds of prey exploit this, with hawks timing early flights to coincide with the exposure of unwary prey in clearings. For insectivorous birds, dawn is a feast. Moths and beetles returning to cover are intercepted in large numbers. This transfer of energy from nocturnal to diurnal food webs marks a critical pulse in the daily cycle, fueling the productivity of daytime species. The social dynamics of dawn are equally striking. The chorus of birds, often dominated by males, is not merely song but strategy. Vocal performance at this time signals territory ownership, health, and readiness to breed. Because light levels are still low, visual displays are less effective. Sound becomes the dominant medium. Research shows that species time their entry into the chorus according to foraging strategies and risk levels. Larger birds often sing earlier, while smaller species delay until visibility reduces predation risk. The layered structure of the dawn chorus encodes ecological hierarchies within its overlapping calls. For humans, the first veil of dawn has long carried symbolic meaning. Ancient cultures regarded it as a sacred interval when night spirits retreated and day guardians awoke. Rituals timed to sunrise often began before the first rays appeared, aligning human activity with the forest's awakening. In literature and art, dawn is frequently depicted as renewal, a washing away of shadows, a promise of continuation. Yet the ecological reality is more nuanced. Dawn is not only a beginning, but also an ending, a moment of overlap where two communities, nocturnal and diurnal, share the forest in fragile equilibrium. Plants also experience dawn as a moment of negotiation. While some species anticipate sunrise by opening stomata, others delay. Conserving water until full light ensures efficient photosynthesis. In tropical forests, dew captured overnight drips from canopy leaves to understory plants, delivering hydration precisely when it is needed most. These micro-events, repeated daily across billions of leaves, sustain entire communities of organisms that depend on moisture, arriving not as rain, but as the quiet offering of dawn. As light strengthens, the nocturnal world recedes. Bats spiral back to roosts in hollow trees or caves, their silhouettes vanishing into shadowed retreats. Owls withdraw to dense branches, becoming nearly invisible against the bark. Amphibians slip back beneath logs and leaf litter, their moist skins protected from the coming dryness of day. This retreat is not defeat, but rhythm, an ancient cycle where night's specialists cede space to days. Diurnal creatures waste no time in seizing the new conditions. Bees and butterflies warm their flight muscles in the first rays, visiting flowers just opening to the morning. Deer step cautiously into meadows, grazing while mist still veils their presence. Pre-dawn silence transforms into a chorus of activity. Wings beating, insects buzzing, mammals rustling through undergrowth. The forest feels as if it exhales, releasing the tension accumulated during the long hours of darkness. The shift from night to day also resets the forest's energy balance. Photosynthesis begins anew, converting sunlight into sugars that will fuel growth and sustain food webs. The first veil of dawn is therefore both a symbolic and literal renewal. Nutrients cycled through decomposition at night, redistributed by fungi and microbes, are taken up by roots just as photosynthetic processes resume above ground. The exchange between soil, plant, and sky is resynchronized, ensuring continuity across diurnal cycles. Culturally, dawn has always been a metaphor for beginnings, but within the forest it is better understood as a hinge, a moment of overlap rather than replacement. The night does not vanish instantly. It lingers in shaded understories, in cool hollows, in the behaviors of species still reluctant to yield. Similarly, the day arrives gradually, asserting itself through growing light and heat rather than sudden dominance. This coexistence gives dawn its unique quality, a merging of two worlds instead of a clean division. Modern research underscores the ecological importance of this transition. Satellite observations confirm that plant photosynthetic activity begins earlier than sunrise suggests, as circadian rhythms prime chloroplasts in anticipation. Acoustic monitoring of dawn choruses reveals consistent patterns that can be used as bioindicators of ecosystem health. Even atmospheric chemistry changes rapidly at dawn, as reactive compounds produced at night are broken down by the first photons. To scientists, the first veil is a data-rich interval, offering insights into resilience, stress, and adaptation. For those who witness it directly, however, dawn remains a moment of quiet awe. To stand in a misted forest as the first light threads through the canopy is to feel both small and connected. Small in the face of vast cycles that long predate humanity. Connected because those cycles still enfold us. The forest at dawn does not simply awaken. It reveals continuity, reminding us that night and day are partners in sustaining life. When you next walk beneath trees or pause in the quiet of a forest, remember, you are part of these cycles too. Every breath of mist, every ray of dawn carries the same life that flows through you. The forest is never apart from us. It is within us. And tomorrow, dawn will return, laying its light across the forest floor,